Hi there. Welcome to this lecture series on matrix algebra. This is lecture 18. The topic is determinant. We will spend about 3 lectures on determinant. This we call lecture A on that topic. And this is part 1. So we will introduce some basic properties of the determinant and on how to compute a determinant. Okay, let's get started. The determinant is a number associated with an n by n matrix. It's a magic number. I say that because I'm cheating a bit. So we will talk about this number and talk about how to compute it, and in some cases its interpretation of that number. Okay, and a really deep, in-depth definition. We will skip that for now. Okay, so it's defined for only square matrix. Let's call the matrix A, and the dimension is n by n. And for a 2 by 2 matrix, this determinant is computed as following. So determinant of matrix A in this form will be A times D minus B times C. So you can think of this diagonal product minus that diagonal product. Some quick example, if the matrix is like this, then the determinant would be 2 times 5, 10, minus negative 3, so plus 3, so you get 13. And this one would be 0 times 7, that's 0, minus negative 8, which is 8. And now for a general n by n matrix A, the exact formula to compute the determinant is rather complicated. So we will now introduce a way of computing the determinant A using more the properties of the determinant. So we will now go through a sequence of the properties. First one is that if the A matrix is upper triangular, then the determinant A is the product of all its diagonal elements. So let's say this is the A matrix and it is upper triangular. What does it mean is under this diagonal line, everything is 0. In that case, the determinant of A is the product of all the elements along the diagonal line. So it's this product. Okay, we can take some quick example. Let's say we have a 3 by 3 matrix like this, and we recognize that it's upper diagonal. So we identify the diagonals. That's 2, 5, negative 1 in red. And you multiply those 3 numbers, you get negative 10, and that is the determinant. And then, for example, this matrix here, which is 4 by 4, it's upper diagonal. And then we look at the diagonal elements in red, and then we see one of them is 0. So you multiply all of them, you'll get 0. So we are very happy with this property because now we recall that, and in previous lectures, we talked about matrix in reduced row form. For every n by n matrix, we can perform basic operations and put it into a reduced row form. And in reduced row form, the matrix is upper triangular. Now we need to understand what happens to the determinant if we perform one of those basic elementary row operations. So let's see. First one, if we multiply a row of A by a constant C, what happens to the determinant? Well, the determinant simply becomes multiplied by C as well. So let's say this is the A matrix, and then I multiply the ith row here by C. I get this new matrix. I call it B. Then the determinant of B is just C times the determinant of A. So a quick example. This is the A matrix, and then we multiply the first row by half. So we get that, and we call this matrix B. Then the determinant of B is exactly half times the determinant of A. Now the third property is about the operation of multiple of a row is added to another row. And this operation does not change the determinant. So the determinant of a matrix being performed this elementary operation is the same as the determinant of the A. So we can also take an example. So this is our A matrix, and then what we do here would be on the second row, we'll take the first row, multiply by -2 and add it on top, and then the second row become like that, and then we call this matrix B. And then thanks to this property, then we know the determinant of B is the same as the determinant of A. Now the last property of those elementary operations, this is that you switch the order of two rows. So if you do that, any two rows, if they are switched, then the determinant will change sign. Say, for example, we have an A matrix like this, and then we switch the first and the third row. So you see these are now different. This one is from here and this is from here, so we switch them. We call that B. Then we know the determinant of B is a negative of determinant A. Okay, so these properties now provide us an algorithm to compute the determinant of a general n by n matrix. So what we do will be, we will be performing elementary row operations on the A matrix, and then eventually put the matrix A into a reduced row form. Let's call that matrix B. And now, since B is upper triangular, then the determinant of the B is just the product of the diagonal elements, and this can be quickly computed. Now, knowing the determinant of B, now we can use the three properties D2, D3, and D4, and then we can use that and go back and find the determinant of A. Okay, so now we're going to take an example. We consider an A matrix, a 3 by 3, like this. Now we will go through elementary operations, row operations, to put this matrix into reduced row form. Okay, so we'll do the following. So looking at the A matrix, there is a 0 here, so we will do switching the first row with the second row. So E, 1, 2, and then we get a matrix like this. And second, we will make this to be 1. So we'll multiply the first row by -1/2. And if we do that, then I'll get 1, -2, -3, and we copy the rest. In the last step, I will be adding on top of the third row, because I want to make this 0. So I multiply row 1 by 2 and add this on top of row 3, and I'm very happy to see this becomes 0 and this becomes 0, because -4 plus 4 becomes 0. Okay, then I see that this is a already reduced row form, and that's we call the matrix B. So we can collect what we have done. So B is starting from A, and 1 operation, 2 elementary operation, and 3 elementary operation, and we reached B. And now, since B is upper triangular, the determinant is just the product of the diagonal elements, which we found quickly, and it equals 4. And let's take a look at each of the elementary operation. This one, switching the row from 1 and 1 and 2, that will change the sign of the determinant. And then multiply it with negative 1/3 on the row 1. We'll multiply the determinant by negative 1/3. And then the last one, and it does not change the determinant. Now we can collect all of these, and we write now the determinant of B would be the determinant A, and then this one will give us a negative 1 sign because it switches, and this one multiplied by negative 1/3, and this one does nothing. So we have this identity. And then we can go back. We can express determinant of A in terms of determinant B. Then we see that that's 3 times determinant of B. And this one determinant of B is just 4. So we get 3 times 4, which is 12. So we have found the determinant of A is 12. Okay, so we see that the amount of work to be performed to find the determinant is the same, almost the same as the amount of work needed to put a matrix into a reduced row form. And the rest in these are less heavy computations. Okay, so that's it for this part of the lecture, and then for the second half we will take more examples and discuss in some more details. Okay, so I hope you enjoyed this part, and I'll see you later.